Welcome to the Deep Dive, where we unpack complex topics using source material you provide. Today, we're taking a deep dive into sources exploring decision trees and related methods in machine learning.
Yeah, this is a really interesting area. It shows how surprisingly simple structures, these tree-like things, can actually make pretty powerful predictions and classifications.
Right, like a flowchart almost.
Exactly. And what's maybe even cooler is how combining lots of these simple trees can lead to, well, much more powerful results, much more accurate, much more robust.
Absolutely. And we've got a good set of sources here. They cover the basics, what is a decision tree, but also how you build them, how you avoid common problems like overfitting.
That's a big one.
Definitely.
Yeah.
And then getting into the more advanced stuff, these different ways to combine trees, things like bagging, random forests, boosting, BART even,
Yeah.
the whole ensemble family. So our goal today is really to walk you through this material. We want to highlight the key ideas, pull out some maybe surprising insights from the sources, and just make sure the practical side of it makes sense. Okay, let's unpack this then. So starting right at the beginning, what's the basic idea? A decision tree in machine learning.
Okay, so at its core, think of it like a flowchart for your data. You have some data point, right? And you want to classify it or maybe predict a value for it.
Uh,
You start at the top, that's the root node, and there you test some feature, some attribute of your data.
like, is income over 50K? Something
Yep.
like that.
Exactly like that. And based on the answer, yes or no, you follow a specific branch down the tree,
Okay.
and then you hit another node and you test another attribute. Or maybe the same one with a different value. You keep going down, following branches,
Until you can't go any further.
right, until you hit what's called a leaf node or a terminal node. That's it. That node gives you your final answer, the classification, or the predicted number.
So geometrically, what are these trees doing? The sources talk about dividing the predictor space.
Yeah, that's a good way to visualize it. All the possible combinations of your input variables, that's the predictor space. The tree carves this space up into distinct boxes, basically. Rectangles, non-overlapping regions.
And everything that lands in the same box gets the same prediction.
That's the idea. Every data point that follows the same path to the same leaf ends up in the same region and gets treated the same way by the tree.
So how does that prediction look different if it's a regression tree versus a classification tree?
Good question. So for regression, where you're predicting a number, like house price or salary, every observation that lands in a particular leaf gets the same predicted value. And that value is usually just the average, the mean of the response values for all the training data points that fell into that same leaf.
Okay, the average of the stuff that ended up there during training makes sense. And for classification, predicting categories like spam or not spam.
For classification, it's simpler in a way. Instead of an average, the leaf node just assigns the class that showed up most often among the training examples in that region.
So majority rules in the leaf.
Majority rules. If most emails in a leaf during training were spam, any new email landing there gets called spam. Simple as that.
And visually, people usually draw these upside down, right? Root at the top.
Yeah, it looks a bit weird at first, but it makes sense if you think of the data flowing down from the root.
Okay, so how do we actually build one? How does the algorithm decide, which variable to test at each step and what cutoff point to use?
Right, that's the key part. The process is often called recursive binary splitting.
This is complicated.
It sounds it, but the idea is fairly straightforward. You start at the top with all your data. The algorithm looks at every predictor variable you have and every possible split point for each of those variables.
Wow, okay. That sounds like a lot of possibilities.
It can be. And it's trying to find the single best split, one variable and one cutoff value that divides the current data into two groups, the two child nodes, in the best possible way.
And what does best mean here?
Best usually means making the two resulting groups as pure or homogeneous as possible. For regression, that typically means finding the split that minimizes the total residual sum of squares, RSS, across the two new nodes. You want the data points within each new node to be close to the node's average value.
And for classification?
For classification, you use different measures like the Gini index or entropy. These measure node impurity, basically, how mixed the classes are within a node. You want the split that results in the purest child nodes, ideally nodes containing mostly instances of a single class.
The sources also call this process greedy. Why is that term used?
Yes, that's important. It's greedy because at each step, the algorithm chooses the split that looks best right now, the one that gives the biggest immediate improvement in purity or reduction in RSS.
But it doesn't look ahead.
Exactly. It doesn't consider whether a split that looks slightly worse now might actually lead to a much better overall tree structure a few steps down the line. It just takes the best local step. It's short-sighted, in a way.
Let's make this concrete with that baseball salary example from the sources. That was pretty clear. They used years in the league and hits last year.
Yeah, that's a great simple example. So a regression tree built on that data first splits on years 4.5. That's the top level decision.
Okay, so experience is the first big divider.
Seems to be in this model. Then only for the players with 4.5 years or more, it makes another split based on hits 117.5.
And that creates the 3 boxes or leaves.
Right. Region 1, the less experienced guys, 4.5 years. Region 2, the experienced guys, 4.5 years, but with fewer hits, 117.5. And Region 3, experienced guys with lots of hits, 117.5.
And the predicted salaries were quite different, weren't they? Like roughly 165K, 400K, and over 800K.
Exactly. The predicted mean log salaries translate to those dollar amounts. What's really neat is the interpretation, like you said. Years is dominant initially, but if you have experience, then hits matters a lot for salary. If you don't have much experience, hits don't seem to factor in, according to this simple tree.
That clarity is definitely appealing. But then the sources immediately warn about overfitting. What's going on there?
Right, the big danger. Overfitting happens when the tree gets too complex, because it keeps splitting and splitting, trying to make those nodes purer and purer on the training data.
It starts fitting the noise.
Exactly. It fits the random fluctuations and quirks specific to that one training set, not just the real underlying pattern. It essentially memorizes the training data.
And the problem is that noise isn't going to be there in new data.
Precisely. So the tree looks great on the data it was trained on, maybe gets near perfect accuracy, but when you give it new, unseen data, it performs poorly because its rules are based on noise. You see this in plots. Training error goes down and down as the tree grows, but test error hits a minimum and then starts going back up.
Okay, so how do we stop the tree becoming too complex? How do we fight overfitting?
The main weapon is called pruning. There are 2 broad ideas. One is pre-pruning. Try to stop growing the tree early, maybe based on some statistical test or a depth limit.
But that sounds hard. How do you know when to stop?
It is hard. It's tough to know the optimal stopping point in advance. So the more common approach, and often more successful according to the sources, is post-pruning.
So you let it overfit first?
You grow a really big, complex tree first, let it fit the training data really well, maybe even too well.
And then trim it back, like pruning a rose bush.
Kind of, yeah. You prune it back, cutting off branches to create a smaller subtree. The goal is to find the subtree that has the best balance, fits the data reasonably well, but is simple enough to generalize well to new data. You're looking for the subtree with the best estimated test error.
Okay, but a big tree must have like thousands of possible subtrees. You can't check every single one.
No, you definitely can't. That's computationally infeasible. So techniques like cost complexity pruning, sometimes called weakest link pruning, are used.
How does that work?
Instead of trying all subtrees, it generates a specific sequence of best subtrees indexed by a complexity parameter, usually called alpha. Alpha essentially adds a penalty for the number of leaves in the tree. As you increase alpha, the penalty gets bigger, and the algorithm finds the best subtree for that level of penalty, which will be smaller and smaller.
So you get a range of trees, from tiny to the original large one.
Exactly, a nested sequence of subtrees, and then you need a way to choose which one is best.
And that's where cross-validation comes in.
That's where cross-validation comes in. You use your training data, maybe split it into k-folds, and for each tree size or each alpha value in that sequence, you estimate what its error rate would be on unseen data using the cross-validation procedure.
And you pick the tree size that gives the lowest estimated error on average across the folds.
Precisely. Algorithm 8.1 in the sources basically outlines that. Grow a big tree, use cost complexity pruning to get the sequence, use cross-validation to pick the best alpha size, return that subtree.
The sources also mention another approach, rule post-pruning, like in C4.5, converting the tree to rules first. That sounds different.
Yeah, it's an interesting twist. You grow the full tree, then you translate every path from the root to a leaf into an if then rule. Like, if years 4.5 then predict salary equals 165K, you end up with a set of rules, one for each leaf.
And then you prune the rule.
Yes, you prune the rules individually, maybe removing conditions from the IF part if they don't seem to help, or even removing entire rules.
Why do it that way? What's the benefit over pruning the tree directly?
The sources mention a few things. One, it can be more flexible because the pruning decision for a condition can depend on the rest of the rule, kind of like context. A node might be useful in one path but not another. Two, it sort of flattens the hierarchy. You don't have this distinction between splits near the root and splits near the leaves anymore. They're all just conditions and rules. And three, some argue that a set of rules can be easier for humans to read and understand than a big tree diagram.
Let's look at that car seats example they used. Predicting high sales, a classification problem. They tried this cost complexity pruning.
Right. So they grew a big tree. It had 35 leaves and got about 73.5% accuracy on their test set. Then they used cross-validation to find the best pruned tree size according to the cost complexity sequence.
And what size did CV pick?
It picked a tree with 30 leaves, so slightly smaller.
Okay. And did the 30-leaf tree do better on the test set?
Well, interestingly, no. The 30-leaf tree got 72.0% accuracy on that same test set.
Huh. So pruning actually made the test performance slightly worse in that specific instance.
It did, and that's a really important point the sources make. Pruning, guided by cross-validation, is designed to select a model complexity that should, on average, generalize better. But CV itself is an estimate based on the training data folds. It's not guaranteed to pick the tree that performs best on one specific held-out test set. It shows there's still some variability involved. Pruning is a good heuristic, not a magic bullet.
Right. Okay, so single trees are interpretable, but maybe a bit shaky, high variance, sensitive to the exact training data, which leads us naturally to combining these ensemble methods. This feels like where the real power comes in.
Absolutely. If a single tree is like one expert opinion, an ensemble is like asking a whole committee of experts. You combine their insights, the single tree becomes the basic building block.
And one of the first big ideas here is bagging. B-A-G-G-I-N-G. Bootstrap aggregation.
Right. The intuition comes from statistics. Averaging a set of measurements reduces the variance, makes the average more stable than any single measurement.
Okay.
But in machine learning, we usually only have one training set. We can't just get multiple independent data sets to train independent trees on.
So bagging fakes it.
Sort of. It uses bootstrapping. Remember, that's sampling with replacement from your original training data. You do this many times, say 100 times, creating 100 slightly different versions of the training set.
Because some data points get picked multiple times, some not at all, in each bootstrap sample.
Exactly. Then you train a separate decision tree on each of these bootstrap data sets. And crucially, these trees are usually grown deep. You don't prune them.
Why not? Don't they overfit?
The individual trees probably do overfit. They likely have high variance. But because they're trained on different data samples, their errors and the ways they overfit tend to be somewhat different, somewhat uncorrelated.
Ah, okay.
So when you combine their predictions, either by averaging the predicted values for regression or by taking a majority vote of the predicted classes for classification, those individual variances tend to cancel each other out. The final bagged prediction is much more stable, much lower variance than any single tree's prediction would be.
Okay, so bagging, bootstrapping, plus deep trees, plus aggregation, averaging voting, reduces variance. What about random forests then? How do they improve on bagging?
Random forests take bagging and add one more clever twist, specifically designed to make the trees in the ensemble even less similar to each other, to decorrelate them further.
Why is that important?
Well, think about standard bagging. If you have one or two really, really strong predictor variables, like yours was in the baseball example, that variable might be chosen as the very first split in almost every single tree, even across the different bootstrap samples.
Right, because it's just the best predictor overall.
Exactly. But if all your trees start with the same split, they end up being quite similar, quite correlated. And averaging predictions from highly correlated models doesn't reduce variance nearly as much as averaging predictions from less correlated models.
Okay, so random forests force the trees to be different. How?
At each node, when the algorithm is considering which variable and split point to use, it doesn't look at all the available predictor variables. Instead, it randomly selects only a subset of the predictors.
Oh, interesting.
Yeah. So maybe there are 20 predictors total. At a given split, the algorithm might randomly pick, say, 5 of them. It then finds the best possible split only among those 5.
So it might be forced to use a variable that isn't the absolute best overall, just the best within that random subset.
Precisely. This prevents one or two dominant predictors from controlling the structure of all the trees. It forces more variety into the ensemble. A common setting is to consider M-score-TP predictors at each split, where P is the total number of predictors.
That's neat. So bagging introduces randomness via rows, bootstrapping. Random forests add more randomness via columns, predictor subset selection.
You got it. And that extra randomness, that forced decorrelation, is often why random forests outperform basic bagging, especially if you have strong predictors.
Okay, bagging and random forests build trees kind of independently, in parallel. Then there's boosting. The sources say that's sequential.
Totally different philosophy. Boosting builds trees one after another in a sequence, and each new tree is specifically designed to fix the mistakes made by the trees that came before it.
Fix the mistakes.
It focuses on the data points where the current ensemble is doing poorly. Essentially, each new tree tries to predict the residuals, the errors left over from the combined prediction of all the previous trees. It's like assembling a team where each new player's job is to cover the weaknesses of the existing team.
So it's learning slowly, iteratively improving.
Exactly. It's often called a slow learning approach. You typically use very simple trees in boosting, sometimes just stumps with only one split, and each new tree makes only a small incremental improvement to the overall prediction, usually weighted by a learning rate parameter.
So there are parameters to tune here, like the number of trees, that learning rate, tree depth.
Yes, those are key. The number of trees, or boosting iterations, the learning rate, often called shrinkage, lambda, which controls how much impact each new tree has. Smaller lambda means slower learning, often better, but needs more trees, and the maximum depth or complexity allowed for each individual tree.
Now, you said earlier that bagging and random forests tend not to overfit much as you add more trees. What about boosting?
That's a critical difference. Boosting can overfit. Because it's so focused on chasing down those errors on the training data, if you let it run for too many iterations or use too high a learning rate, it can start modeling the noise. The sources show plots where the test error for boosting starts to increase after a point.
So you need to carefully tune the number of trees, probably using cross-validation again.
Absolutely. Finding the right stopping point is crucial for boosting.
And finally, briefly, the sources mention BART-Bayesian additive regression trees, another ensemble.
Yeah, it's another one based on summing up predictions from multiple trees. Like boosting, it often involves iteratively fitting residuals. But it uses a Bayesian probabilistic approach to guide the tree structures, using random changes in prior beliefs. The sources suggest it's quite good at resisting overfitting.
The sources gave some comparisons on real data sets. What did those show? Any clear winners?
Well, it depends a bit on the dataset, as you'd expect. On the HART data, random forests using that SCORT-TP predictor subset rule did tend to outperform bagging as they added more trees, which supports the idea that the decorrelation helps.
Okay.
On some gene expression data, boosting with very simple depth 1 trees, stumps, actually did slightly better than boosting with depth 2 trees in random forests. So sometimes simpler is better, especially in boosting.
Interesting.
And then on the Boston housing data, predicting house prices, bagging, random forests, and boosting all ended up with pretty similar test errors. Bagging was maybe slightly better in their run, but they were all in the same ballpark. Sometimes the specific ensemble method matters less than just using an ensemble.
Right, the power of the crowd. And those variable importance plots they showed are quite helpful, aren't they, to see what factors the models relied on?
Definitely. For Boston housing, it highlighted things like ILSTAT, lower status population percentage, R number of rooms, AE ratio, pupil-teacher ratio, as being really important drivers in the models. For the HART data, it was things like THAL, the thalassemia measure, call, number of major vessels seen in fluoroscopy, chest pain type. It gives you a high-level summary of what features mattered most to the ensemble's predictions.
So let's pull back again. Why have these tree-based methods, particularly ensembles, become such a cornerstone of modern machine learning?
Well, several reasons. One is just raw flexibility. They can capture really complex, non-linear patterns in the data that simpler models like linear regression just can't handle. That figure 8.7 in the sources showing how different methods partition the space really illustrates that well. Trees can create these intricate decision boundaries.
And we talked about interpretability, at least for single trees.
Yes, that's a big selling point. Single trees are easy to visualize and explain. Even some ensembles, like boosted models with shallow trees, can offer some level of interpretability, especially with those variable importance plots. And some people feel they mimic human decision-making more closely than, say, linear equations.
But the sources also brought up this concept of inductive bias. Can you unpack that a little?
Sure. Inductive bias is basically the set of assumptions a learning algorithm makes that allows it to generalize from the training data to unseen data. It's the algorithm's policy for making predictions when it hasn't seen that exact input before.
Okay.
Decision tree algorithms like ID3 are described as having a preference bias or a search bias. They prefer simpler trees, shorter trees, trees with fewer nodes. They'll choose a simpler tree over a more complex one if both fit the training data equally well.
But they don't completely rule out complex trees.
Right, that's the key difference from restriction bias, which strictly limits the kind of hypotheses the algorithm can even consider, like linear regression only considering lines. Preference bias is often seen as better because it keeps the door open to finding a complex pattern if the data really supports it, but defaults to simplicity otherwise.
And that preference for simplicity sounds a lot like Occam's razor.
It's directly related. Prefer the simplest hypothesis that fits the data. The sources touch on why this might be a good strategy. One argument is statistical. There are just mathematically fewer simple models than complex models. So if you find a simple model that fits your data well, it's perhaps less likely to be a random fluke than finding a complex model that fits, because a complex model could probably fit any data set, including noise.
But defining simplicity can be tricky, right?
Very tricky. Is a tree with fewer nodes simpler, or one with shallower depth? It depends on your representation. It's a deep philosophical issue, actually.
It reminds me of that polynomial fitting example that often comes up in ML introductions.
That's a perfect parallel. You have noisy data points that follow some underlying curve. A simple, low-degree polynomial gives a reasonable fit, capturing the trend. A super high-degree polynomial can wiggle frantically to pass through every single point, perfectly fitting the noise.
But it generalizes terribly.
Exactly. It's completely useless for predicting new points. That's overfitting, just like with trees. And the solutions are analogous. You use regularization, like penalizing large coefficients in the polynomial, or cross-validation to pick the right degree of complexity. With trees, you prune or you carefully tune your ensemble parameters. It's the same fundamental battle against overfitting by managing model complexity.
So thinking about the history of machine learning, from early perceptrons, then backpropagation enabling neural networks, now deep learning dominating many areas.
Yeah.
Where do tree ensembles fit in this bigger picture? Are they still relevant?
Oh, absolutely relevant. Hugely relevant. While deep learning has achieved incredible things, especially with unstructured data like images and text, tree-based ensembles like random forests and gradient boosting are often still the state of the art, or at least extremely competitive, for working with structured tabular data, the kind you find in spreadsheets and databases.
And they often require less data and tuning compared to deep neural networks.
Often, yes. And they tend to be much more interpretable. So they are a vital, powerful part of the modern machine learning toolkit. They offer a fantastic balance of predictive power, flexibility, and often better interpretability, depending on the specific method and problem.
Wow, okay. We've really covered a lot of ground in this deep dive. We started with the basics, what a decision tree is, how it works like a flowchart, splitting the data space recursively.
Yeah, and looked at how that greedy splitting works, using examples like the baseball salaries to see how it picks variables and creates those regions.
Then we tackled that crucial issue of overfitting, how trees can get too complex, and explored pruning strategies like cost complexity pruning, using cross-validation to find the right balance. We even saw with the car seats data that pruning doesn't always guarantee a better score on one test set, but it's about finding good generalization.
Right. And then we moved into the really powerful ensemble methods, bagging using bootstrapping and averaging to cut down variance, random forests adding that extra layer of randomness with feature sampling to decorrelate trees even more.
And boosting, that's sequential approach, learning from errors, building strong models piece by piece, though with a risk of overfitting if you're not careful. Plus a quick mention of BART.
We saw how they compare on different data sets. Sometimes RF is better, sometimes boosting, sometimes they're similar, and how variable importance plots can give us clues about what's driving the predictions. These are really flexible tools.
Absolutely. They handle complexity well and have built-in ways to fight overfitting. Okay, so here's something to chew on. We talked about Occam's razor and the preference for simpler models. How does that idea hold up when we start using these massive ensemble models? A random forest might have 1,000 deep trees. A boosted model might have thousands of iterations.
That's a great question.
We gain incredible predictive accuracy, often state-of-the-art. But have we completely thrown simplicity and therefore maybe interpretability out the window? Is that inherent trade-off complexity and power versus simplicity and understanding always the right one to make? Where's the balance?
Definitely something to think about as you continue your own deep dives into these methods.